Hey guys, welcome to video 94. We're going to continue our discussion of thyristors by looking at some common applications, and we're going to start with a circuit called a relaxation oscillator. To understand how this oscillator works, we'll assume that we've just connected the battery up to the circuit. The capacitor has no charge, so there's no voltage drop across the four-layer diode, so it's behaving like an open circuit. The capacitor begins charging through R1, and it follows this exponential charge curve that's described by this equation. The instantaneous capacitor voltage is equal to V in times 1 minus e to the negative t over tau, where tau is the RC time constant, is just R1 times C1. Now, if we didn't have a four-layer diode in the circuit, the capacitor would just charge up to its final value and sit there. But assuming the breakover voltage is less than V in, we're going to hit the breakover voltage, at which point the four-layer diode becomes a very low resistance. It discharges C1 very quickly, and the voltage drops to the valley voltage of the four-layer diode, at which point it becomes an open circuit again, and this charge-discharge cycle just repeats over and over again. Now let's take a look at how we can derive equations for the period and frequency of this waveform. We're going to make a simplifying assumption at the outset, and that is we're going to disregard the time interval it takes to discharge the cap from the breakover voltage to the valley voltage. When the four-layer diode turns on, it's got very low internal resistance, so it'll discharge this capacitor very quickly, and this time interval is so short that we can neglect it without adding too much error to the analysis. So now if we take this exponential charging equation and we solve it for the time it takes to go from the valley voltage to the breakover voltage, we get this messy thing over here. We've got some ugly compound fractions, but they can be cleared relatively easily, and I'm going to leave that as homework for you guys. And when we do that, we get this nicer looking equation here. Now, remember, frequency is just the reciprocal of the period, so if we take the reciprocal of this equation, we've got our frequency equation, and you can see that the frequency is dependent on the input voltage as well as the diode parameters and the RC time constant. So we've got a lot of variables in here that can affect the frequency. And because of this, we wouldn't use a relaxation oscillator in any application that required precision timing. We'd probably be lucky to get a frequency within about 5 or 10% of the actual frequency using this equation. Now, there are things we can do to eliminate the dependency on the input voltage, for example. And if you go back and look at video 50 where we analyzed the 555 timer, you can see an example of some things that can be done with circuits that are basically relaxation oscillators that make them a little bit more predictable. Now, I built this circuit and did a few scope captures using different power supply voltages, so let's go on over to the next slide and take a look at those results. In this example, I've got a power supply of 250 volts, my RC circuit is 100K and 0.01 microfarads, and I'm using a four-layer diode with a breakover voltage of 32 volts and a valley voltage of 12 volts. Now, really, this isn't a four-layer diode, it's a TRIAC, but we're treating it like a four-layer diode, so it behaves exactly the same in this circuit. And here's our formula for the oscillation frequency. Plugging in the values for this circuit, we get a theoretical frequency of about 10.3 kilohertz. Connecting the scope up to measure from anode to cathode, this is the waveform we get, and we're reaching a breakover voltage of about 34.7 volts. That's our Vmax value shown here. And our valley voltage is about 12 volts. We've got a period of roughly 99 microseconds, and the frequency is approximately 10.1 kilohertz. I labeled it here, but we can also see it over here, and that's pretty close to the calculated frequency, so we're not doing too bad here. Now, 250 volts is a pretty high power supply voltage, so I thought I would try this with a little bit lower voltage, and I reduced it to 45 volts, and this was the display we got. Our breakover voltage dropped a little bit to 34 volts. These 4-layer diodes are a bit nonlinear and they tend to have some hysteresis, so you will get a little bit of variation of parameters when you change things like power supply voltage or RC circuit values. But anyway, here we've got a breakover of 34 volts and the valley voltage is still about 12 volts, and this gives us an oscillation frequency of about 920 hertz. When I plug my new values into the formula, I get a theoretical frequency of 1.1 kilohertz. So it's not quite as accurate as it was in the previous example, but it's not too bad considering all the variables we have to work with. Now, the relaxation oscillator is one application for 4-layer diodes, but there are others, and one of the most significant is to use it as a trigger diode. That's why they're called trigger diodes sometimes, and that's what we're going to look at next in this circuit, which is an old school phase control light dimmer. Light dimmer circuits are considered relatively simple, but really there's a lot of stuff going on here, and I'm going to try and explain how this works as clearly and concisely as possible. The main idea is that we're going to control the brightness of this lamp by varying the average current flow through it with this SCR. Now, I'm going to start out with a qualitative description of what's going on here, so you can ignore all these equations for the time being. And let's come over here and look at this RC circuit. With a 50K pot and a 10K fixed resistor, the minimum resistance here is 10K. The maximum resistance is 60K. Now, we need a minimum resistance that's not zero to limit the current flow into the gate of our SCR, and that's the function of R1. 10K ohms works pretty well in this application. It limits our gate current to something that's not going to harm the SCR. The SCR we're using here has a breakover voltage of 500 volts, so normally we couldn't turn it on with a 120 volt RMS AC line. But remember from the previous video, we know that if we inject a gate current, we can reduce the breakover voltage of the SCR. Now, from a design or analysis standpoint, the problem here is that the turn-on characteristics of the SCR in terms of gate current are very ill-defined, and that's why we use a 4-layer diode in series with the gate. Whenever the capacitor voltage rises to the breakover voltage of the 4-layer diode, we get a large current pulse into the gate of the SCR, and as long as we're operating on this positive half cycle of the AC line, the SCR will be turned on, and it'll stay turned on until the current through the SCR drops below the holding current, and that happens pretty darn close to zero crossing here in the negative direction. So we're controlling the brightness of this lamp by varying the average current flow through it. The sooner we turn the SCR on in this positive half cycle, the more conduction we have and the greater the brightness. If we turn it on later in this half cycle, we get lower average current and lower brightness. Now, when the AC line voltage drops to about zero, the SCR shuts off and we get no conduction for this half of the cycle. And it's basically a half-wave controller. And the fact that the SCR turns off automatically at zero crossing is called auto commutation. Now, looking at the waveforms we've got here, we're assuming that we're delaying turn on of the SCR for 2.5 milliseconds, at which point we get breakover of the 4-layer diode. The SCR turns on here, and this is the load current waveform we get. At 2.5 milliseconds, we get load current flowing, and it continues roughly until zero crossing of the AC line. It actually turns off a little bit before that because that's where we drop below the holding current of the SCR, but we could ignore that with very little error. Now, traditionally, we characterize the on time of the SCR by using what's called the conduction angle, and that's just the number of degrees for which the SCR is turned on during one cycle of the AC line. The equation for the conduction angle is shown over here in the yellow box, and for our circuit right now, we end up with a conduction angle of about 125 degrees. Now let's go back to our schematic and look at the circuit again. D1 is shown as a 4-layer diode, but I didn't have one. I had to use a TRIAC here. Remember, a 4-layer diode only breaks over in the forward direction. A TRIAC breaks over both directions. So to make this behave like a 4-layer diode, I put a regular 1N4003 in series with it. That way it does break over in the forward direction, but it will not break over in the reverse direction. Now, if we come over to the RC section of this circuit, we'll see why it's called a phase control light dimmer. If we have the resistance set for minimum 10 k ohms, the capacitor voltage is going to increase to the breakover voltage of our 4-layer diode relatively quickly, and we'll turn the SCR on pretty early in this half cycle. If we increase the resistance to maximum 60 k ohms, it's going to take longer for our capacitor to charge the breakover voltage, and we'll delay turn on until much later in this half cycle. Now, because we have an RC circuit, there's going to be a lagging phase shift in the voltage across the capacitor relative to the AC line, and that's why this is called a phase control light dimmer. When we change the resistance, we're going to change the phase lag associated with this voltage, and this way we can delay turn on past the peak over into this negative going portion of the positive half cycle. If we just had a resistor here, we'd only be able to control the turn on within the first quarter cycle. That is somewhere between t equals 0 and the peak of the waveform, which would be what, 4.15 milliseconds or so. Okay, now that might have been kind of hard to follow, so I'm going to explain this again in a slightly different way. If we assumed we had a resistor down here instead of a capacitor, we would just have a variable resistive voltage divider. We wouldn't get any phase shift associated with this voltage, and that would only allow us to control the conduction angle somewhere during the first quarter cycle of the AC line. That is between t equals 0 and t equals 4.15 milliseconds. Now, since we put a capacitor here, basically we've got a low-pass filter, and the output of a low-pass filter is always lagging in phase relative to the input. So in addition to getting the voltage divider, we also have a lagging phase, which allows us to push the trigger point past the peak value over into this second quarter cycle, and it gives us wider range of the conduction angle. Now, all the stuff I have shown here with these waveforms is based on the assumption that the resistance is set for minimum 10 k ohms, and we get maximum brightness with a conduction angle of 125 degrees. But you might be wondering, where the heck did I come up with this? And well, depending on how we approach it, it can be a pretty complex analysis, because we have a sine wave applied to an RC circuit, and we have this nonlinear switching function occurring because of the 4-layer diode. So really, to analyze this accurately, we'd have to use Laplace transforms to account for the sinusoidal and the exponential stuff going on here. But rather than go to that level of complexity, I kind of linearized the circuit, and I treated this as if it was a regular RC circuit that we could analyze with phasor algebra, and then I just calculated the time it took to reach the breakover voltage of the 4-layer diode and put all those pieces together. And really, I guess the best way to explain it is to just go show you the calculations and derivations. And here they are. What I'm going to do here is just walk through my derivations step by step, and hopefully it'll make sense. We'll start with our AC line, which is 120 volts RMS at 60 Hertz, and the instantaneous form is expressed here, where omega is the frequency in radians per second. That's 2 pi f, 2 pi times 60, which is about 377 radians per second. And the peak amplitude of the AC line is just the square root of 2 times the RMS value. That's about 170 volts. So our input voltage equation is shown here, 170 sine 377t volts. In phasor form, if we assume this is our reference, it's going to be 170 volts at 0 degrees. Next, we're going to calculate our capacitive reactance. That's 1 over 2 pi Fc, or 1 over omega c, at an angle of negative 90 degrees. So using 0.22 microfarads for our cap, we get a capacitive reactance of about 12 k ohms at negative 90 degrees. Now, for this example, we're assuming we have the pot set for minimum resistance, so R equals 10 k ohms. And what we'll do next is determine the capacitor voltage in phasor form using the voltage divider equation. So we've got a little bit of coordinate conversion stuff going on here, nothing really too complicated. And in the end, we end up with a capacitor voltage of 131 at negative 40 degrees volts. We could also do this by applying filter analysis equations, but I figured I'll just stick with regular circuit analysis, with the voltage divider and go from there. Next, I'm going to express this phasor in instantaneous form, and that's 131 sine 377t minus 40 degrees. And I've used degrees because I like them better. They're easier for me to relate to, but I'm going to do my calculations using radians. So this minus 40 degree phase angle works out to be minus 0.7 radians, and this would be the form of the equation I'll use for my calculations. Now, this phase lagging voltage is applied to our 4-layer diode, and we know it breaks over at 32 volts. So what we're going to do is substitute that into the equation, solve it for t, and when we go through the algebra, we end up with a time delay of 2.5 milliseconds. So that accounts for the voltage division, reducing our peak voltage from 170 to 131, and a phase lag of 0.7 radians. What I'll do next is determine the value of the AC line voltage when the SCR fires, and we do that by just substituting this time into our line voltage equation, which gives us about 138 volts when the SCR turns on. The SCR remains latched on until the load current drops below the holding current of the SCR, but remember, that's pretty close to when we have zero crossing of the line voltage. So the conduction time, we're calling that T on of the SCR, is T, the period of the AC line, divided by 2 minus the time delay. So that gives us about 5.8 milliseconds of on time per cycle of the AC line. Then we can convert this time interval into degrees by applying this formula, and that works out to give us a conduction angle of about 125 degrees. Now, on the previous page, we had a graph of the input voltage waveform and the load current waveform based on these parameters, and if we go back over just as a refresher, here it is. Now, the input waveform isn't really that useful for us to look at. The load current is, but that's very difficult for us to look at on an oscilloscope. It's hard to measure current. So what I'd like to do is show you the waveform for the anode to cathode voltage under these conditions, and that's shown over here. Looking at the anode to cathode voltage waveform, we can see that the SCR is turned off from t equals 0 to 2.5 milliseconds. At this time, we break over the 4-layer diode, which turns on the SCR and causes it to become essentially a short circuit from anode to cathode, and the voltage drops down to about 0 volts. It stays there until the load current drops below the holding current of the SCR, then it turns on just slightly before zero crossing. Now, we can normally ignore this little glitch in the waveform here, but I'm showing it here just because it's going to show up on the scope, but again, it's normally something we can ignore. Now, the SCR turns off, and for this next half cycle, the line voltage is dropped across the SCR, and we get this entire negative going portion of the waveform, and that continues until we trigger the 4-layer diode again, and this just repeats over and over again. Now remember, the values I have listed here are based on a theoretical analysis of this circuit. I did build it and took some measurements, and I want you to remember our T on here is 5.8 milliseconds. So building the circuit, setting the resistance to 10 k ohms. This is the scope display I got for the anode to cathode voltage. And note that we have a T on of 5.8 milliseconds, which is exactly what we calculated. And that gives us a conduction angle of about 125 degrees. So our actual circuit performance is in really close agreement with the theoretical analysis. Now, the next step in the analysis would be for us to analyze the circuit with the pot set for maximum resistance and minimum brightness. And I'm going to leave that for you guys to do as homework. And I'm just going to show you what happens in the real circuit if we do that. I adjusted the pot for maximum resistance. We've got 60 k ohms, and now our conduction angle decreases to 43 degrees. This is my anode to cathode voltage waveform. Now, as you can see, with a 50K pot in the circuit, we aren't able to reach a high enough resistance to reduce our conduction angle to 0 degrees. We can solve that problem easy enough by simply replacing this with a 100K ohm pot. But for right now, what I'd like to do is show you the circuit in action. We'll actually look at a light bulb, and we'll see the waveforms change as we vary its brightness. This is the circuit with the SCR and the 50K ohm pot set for minimum brightness, and here's the scope display we get. And if we adjust the brightness higher at maximum brightness, here's our oscilloscope waveform. So the waveform for minimum brightness and maximum brightness. Minimum, maximum. So there we see that this simple circuit gives us pretty good control over the brightness of this lamp, but in the video it's pretty hard to see that it doesn't really get that bright, and again that's because we only have a half-wave rectifier here. If we were to replace the SCR with a TRIAC, then we could get full wave control and get conduction on both positive and negative half cycles, and the bulb would be twice as bright at maximum illumination. So that's what we're going to take a look at next. Now here's our circuit where I've replaced the SCR with a TRIAC and the 4-layer diode with a DIAC, although this is really the same device I used before. I've removed the 1N4003, so now we can treat it as the DIAC that it really is. And I've kept the same resistor values and capacitor value for the circuit. Now at maximum brightness with our pot adjusted so that we've got a total resistance of 10 k ohms, these are the waveforms we've got. Here's our input waveform. We still have roughly the same time delay of 2.5 milliseconds until the TRIAC turns on, and we still get the same T on for the first half cycle of about 5.8 milliseconds. We haven't changed the RC time constant or the breakover voltage of this DIAC, so that all stays the same. But the thing that happens is that once we hit the negative going half cycle of the input, the DIAC will trigger on for negative VBO, that is negative 32 volts, will turn on the DIAC, which will trigger on the TRIAC, and then we get conduction for this part of the negative half cycle. So at maximum brightness, this is what the current waveform for our load looks like. And because the TRIAC conducts symmetrically for both positive and negative going portions of the line voltage, we're going to get a conduction angle that's twice that of the equivalent SCR circuit for a given pot setting. And here's the equation to calculate the conduction angle. In this case, it's 250 degrees. For the SCR, we had a conduction angle of 125 degrees. Now, this current waveform is nice because it gives us a good correlation between the waveform and the brightness of the bulb. If we've got a lot of area under this curve, we're going to get a really bright bulb, but it's very difficult to measure current using an oscilloscope. So let's take a look at the voltage drop across the TRIAC. And over here we can make a comparison between the waveforms for the SCR maximum brightness versus the TRIAC under maximum brightness. And you can see that we're getting much wider control over the brightness of the bulb with the TRIAC. Now, if we adjust the 50K pot for minimum brightness, we're going to delay firing the SCR or the TRIAC until about 4.3 milliseconds into the cycle. And here's what the waveforms are going to look like in that case. For the circuit with the SCR, we get a theoretical conduction angle of about 86 degrees. And the theoretical conduction angle for the circuit using the TRIAC is twice that, about 172 degrees. Now, as we saw earlier in the video, when we look at the actual circuit in operation, even though we have a conduction angle of around 86 degrees, the bulb didn't light up with the SCR-based circuit. But that's not going to be the case with the TRIAC because we've doubled the conduction angle, and we'll see even at minimum brightness with the 50K pot, the TRIAC circuit is going to let the bulb light up significantly, and we're going to take a look at that right now. Now, here's our circuit with the TRIAC replacing the SCR, and the 50K pot is set for minimum brightness, and you can see the bulb is lit up a fair amount. Here's the waveform we get on the oscilloscope, and if I adjust the pot for maximum brightness, we can see that it's pretty bright, and here's the waveform we get. So we'll sweep from maximum brightness to minimum brightness, maximum, minimum, and again minimum to maximum to minimum. And we're back. Now what I want to do next is take a look at the actual waveform for the TRIAC control circuit under minimum brightness conditions and compare it to this theoretical waveform. And this is what we get. We have an actual time delay of 5 milliseconds versus the theoretical of 4.3 milliseconds. We have an on time of 3.3 milliseconds versus the theory, which says 4 milliseconds. So we're pretty close, and overall we get a conduction angle of 142 degrees in the actual circuit versus 172 degrees for the theoretical analysis. So it's actually not too bad considering all the approximations I made with the derivation. This is pretty good. And you may have noticed that I superimposed our input line voltage over top of the TRIAC voltage just to make it a little bit easier to see what's going on here. Now, this video has been going on for quite a while, and quite frankly, you'd probably think only a maniac would analyze a circuit like this to this level of detail. And maybe you're right, but we're almost done. So what I want to do next is address the problem of us not turning off this TRIAC completely, and we're going to increase the potentiometer to 100K ohms, and that'll fix it. So here's the circuit with that modification made, and we're going to take a look now at the waveforms we get in the actual circuit with the 100K pot in there. Now I've replaced the 50K pot with a 100K pot, and when it's set for minimum brightness, you can see the bulb is all the way out, and the waveform across the TRIAC is just the AC line voltage. It's not turning on at all. Now if I turn the brightness up, we can see that it gets just as bright as before, and the waveform across the TRIAC looks the same as maximum brightness previously. So that's maximum brightness, minimum brightness, maximum brightness, minimum. And there we go, minimum to minimum, back to maximum. And we're back again, and this wraps up today's video. I know this was a long one, and I went really pretty deep on something that is rarely covered to this level in textbooks, but I thought, what the heck, why not do it? You know, it can't hurt, and you can always skip through parts you aren't interested in. But anyway, that's it for today. Next video, we're going to get into color organs, and that should be maybe a little bit more fun. And I'll see you next time around.